Hi. In this lecture, we're going to interpret the inflection points we've been talking about into business applications where we're going to see them as the point of diminishing returns. So let's start with a classic example. Let x, the input variable, be not the number of items as it usually is, but let's let x be the amount of money that my business is spending on advertising in thousands of dollars. You can imagine that if I spent more money on ads, I would make more total revenue. So then I can consider that my output function, r of x, is going to be total revenue in thousands of dollars. And again here, this r of x does not depend on the number of items that I'm selling, but I want to consider my total revenue as a function of how many dollars x in thousands that I'm pumping into advertising. I'm trying to increase my revenue by spending more money on advertising. Okay, so to make it concrete, let's use this cubic function to model the dependence of our total revenue on the value of how much money we're spending on ads. Now, because I'm not willing to spend an infinite amount of money on ads, let's restrict that domain to between $0 and $40,000. Careful here. We've defined x as the amount of money in thousands of dollars, and the output as well is coming out in thousands of dollars, so every time we get a number, we have to think about multiplying that number by thousands of dollars. $40,000 is the most that I'm willing to spend on advertising, and you can see that if I plot my total revenue as a function of that money spent on advertising, that expectedly, my total revenue is going to increase depending on how much money I pump into the ads. Should I go the full mile and spend all $40,000 I have in my budget on advertising? Should I stop somewhere in between? This is where the concept of the point of diminishing returns is going to come into handy, because the point of diminishing returns is a point at which a marginal quantity is maximized. Now you can see that if I asked you to locate the relative maxima on this function, you can't really find it. The function is always increasing, so it doesn't really have a spot except for the spot at the end where it has like a local relative maxima. Okay? But there is something that I can maximize, and that will be maximized inside this interval somewhere. What is to be maximized is going to be a marginal amount, i.e. a derivative quantity. So what we're going to show here is that if we take the derivative of the function and analyze that, the derivative of this total revenue has its relative max where the inflection point of this function is located. Now remember, inflection points are points where a function will change from concave up to concave down or vice versa. Can you recognize the intervals over which this function is concave up and the interval over which it's concave down, and can you recognize the inflection point? Remember what I said? Concave up is like a cup, concave down like an umbrella protecting you from the rain. And so you can see that it's clearly concave up here, and it's clearly concave up down there. However, it's not so clear to me exactly where does it change sign. Where does that inflection point occur? Well, I really care exactly where it occurs, because that's the point of diminishing returns. That's going to be the place where my r prime has its relative max. Now, before I start caring too much about what r prime is, why don't we talk about what r prime means, okay? And in order to get what r prime means, we have to find out the units. R prime is in units of what? After we figure this out, it should be more straightforward to interpret that quantity. Okay, so the units, every time I say this, they're the y units over the x units. If you can keep that straight, then you should be able to derive the units. The y units is total revenue in thousands of dollars. So r prime is in thousands of dollars. Let's write it as revenue. Let's write it as total revenue dollars in thousands. So you gotta just remember that's in thousands. And the x units here is advertising dollars. So we're gonna write advertising dollars. And that's also in thousands. You see I'm just squishing it in there, but I've tried to write it right here. The x is in dollars, the y is in dollars. So I don't want to write dollars over dollars because they're not the same dollars. They're the dollars I'm putting into ads versus the dollars that I'm getting from my revenue. So that's why I don't want to just write dollars over dollars, because then some people would just be tempted to cancel that out and say it has no units. It does indeed have units. Just like before, it has the units of y over x. So my r prime is in units of total revenue dollars in thousands divided by advertising dollars in thousands. Okay? Now, hopefully that makes it a little bit easier to appreciate the meaning of the derivative, because what the derivative there, r prime, actually means is that if my x increases by 1, which is to say if I decide to pump 1,000 more dollars into ads, then my total revenue will change by r prime, right? So if I put, let me write this down, if I put 1,000 more into my ads, then my total revenue will increase by r prime of x, $1,000. Okay, so that's the interpretation right there. So you can see why that's so important. Maybe this is crowding it up. You know what the x is now. The interpretation of the derivative is that it's the amount that my total revenue will change if I increase my ad spending by $1,000. So this is 1,000 more dollars. Okay, and so that brings us again to the point of diminishing returns. You can see now that r prime is the boost in my total revenue whenever I spend 1,000 more on ads. Now, should I always do that? Is it always going to be exactly the same amount of bang for my buck? Not necessarily. Actually, I would want to consider maybe keep putting money into ads until I hit the point at which this number right here is at its possible maximum that it can be. Because if this number, r prime, was as big as it could be, that would be the most money that I'm getting in my return of revenue for the amount of $1,000 increase in my advertising spending. That's why it's called the point of diminishing returns, because once you find that point at which r prime is maximized, which is going to be right around here somewhere, this is going to be where r prime has its max, and r has an inflection point. That's how we're going to find it, is at an inflection point. If I go past that point, then the amount of return in revenue dollars that I get for each additional amount of spending on ads is going to diminish. So that's why I want to go up to this point of diminishing returns. That's a nice sweet spot where I'm getting the most boost in my revenue for every extra dollar spent in ads. And then after that, I'm really not getting as much as I was before. So, depending on how it's going, maybe I don't need to go all the way. Okay, so let's go ahead and find that point. I can kind of see that it's concave up here. I can kind of see that it's concave down here. But I'm not exactly sure where this is. And so I finally need the calculus. Okay, so let's do it. We're going to take the derivative of that function, and then we're going to take the derivative again. Because this time, I'm not looking for any relative maxes or mins. As you can see from the picture, I don't really have any relative maxes or mins. As much money I want to put in, I'm going to get more money on my return. However, there's that secret sweet spot, the inflection point, where I'm getting the most out of each dollar that I'm spending on ads. So we got to find that, okay? So r of x, I'll just rewrite it right here, is this cubic function. And so we need to set its second derivative equal to 0. So first we'll take its first derivative, just like this. And then we'll take its second derivative, just like this. And then when we've got its second derivative right here, we're going to set that equal to 0 because we know that those are the candidates for inflection points. The point of diminishing returns is going to be an inflection point by definition because it's a place at which the marginal or derivative quantity has its maximum. Okay, and remember, when something has a relative max, what's the value of the derivative when it has a relative max? 0, or does not exist. But so if the derivative is 0, that's the derivative of this. So the second derivative has to be equal to 0. All right, these are my candidates for my inflection points, and so I can solve this out. This is negative 3/5 x is equal to negative 12, and so what do you get out of that is that x is equal to 20. Alright, let's just stop to think about what we're doing here. We got the number x equals 20, and what does 20 mean again? Is that 20 items that I should sell? No, not on this problem. Remember what your x's are for each problem. This is $20,000 of money that I should spend on ads in order to hit this amount of revenue right here, and this is where I'm getting the most bang for my buck on each one of those additional revenue advertising dollars, okay? Oh wait, I spoke too soon. I should really prove that this is actually an inflection point. Now I've inherently shown it here because I can recognize visually that I have a function that's concave up changing into something that's concave down. So I know that this is an inflection point, but just to be fair with the other things that we've seen so far, how you actually prove that it's an inflection point after you've located the candidate for inflection point is that you're going to show that the function actually changes sign there. Not the function, sorry, but the second derivative sign, number line. You want to show that there's a change in the sign of that. Okay? So here we're going to make the r double prime sign number line, and so we have the x equals 20. So over here we could try x equals 0, right? What am I plugging in the x equals 0 to? That function? That's right, the second derivative. You're always plugging the test points into the same function that you've written down the name of the sign number line on. That's because you're trying to find the sign of that function right there. Does that make sense? So we're going to plug in a test point x equals 0 here, and we get 12. Just like I thought, concave up all the way until x equals 20. Then if we plug in a really big number, x equals 30 over here or something, you see that would be negative. Minus, minus, minus. Just as we see on the graph, it's concave down when x is greater than 20. Okay, so let's try to make this sign number line agree with what we know about the first derivative test. Because here, I've told you that the point of diminishing returns is a point at which a marginal amount is maximized, which is to say, the first derivative has a relative max. If the first derivative has a relative max, I could really see this as the r prime sign number line. And I want to see it that way to put it in line with the first derivative test, because although this is the second derivative of total revenue, it is the first derivative of something. It's the first derivative of the marginal revenue. It's the first derivative of the first derivative. So if I want to know when that first derivative has a relative max, I must only look at its first derivative sign number line. I hope you're not getting too confused with this. Okay, so now that's why I can perform the first derivative test right now. I'm going to perform the first derivative test so I can classify this as either a relative min or relative max in the marginal quantity of the marginal revenue. Okay, so use the first derivative test to classify x equals 20 as either a relative max or min for the marginal quantity r prime, which is the marginal revenue. Keep in mind, this is the marginal revenue in the sense that the input or x variable is dollars of advertising. A little bit different than what we usually see it as, but I think you can still refer to it as a marginal quantity. Okay, so let's see. Is it a relative max or min? Function's going up, hits the top, going back down again. So it looks like this is a max by the first derivative test, and it's a max, but it's not a max on the original function, and you can see that. Always confirm with the plot of the original function if that's possible for you. It's not a max there, it's a max in r prime of x. It's where the marginal revenue is maximized, and sometimes maybe that's the best place you want to be. Because you really want to be putting in an extra $1,000 into advertising dollars here when it's not really going to change your total revenue that much. You see, if you put in an extra $1,000 right here, it's going to jump from here all the way up to there. The marginal quantity is really large there. But if you do it over here, it's just going to jump a teeny tiny bit. The marginal quantity is kind of small over there. So sometimes we would prefer the point of diminishing returns over the actual relative max or min of the total quantity. All right, let's go on one more example here. And that's going to be an example in production rate. You can see that derivatives, as I just showed you, can be interpreted as marginal quantities in the total quantities of business. But what if we have some function that describes how fast our workers are producing something? So let's say we have a production function, and what this function is, we'll call it P of T, is going to be the number of items that a worker can produce over T hours on a shift, okay? So let's say T is from 0 to 8, which is to say that 0, that might be like 8 a.m. if it's the day shift, or maybe 4 p.m. for 8. So it depends on what shift it is, but typically you have some sort of 8-hour shift. And this function right here, T is in hours, P of T is going to be the number of items produced. Okay, so if we graph this function, we will expect to see the number of items that a worker has produced over the T hours that they've been working. And let's try to pick out and interpret the point of diminishing returns, and we'll see what that kind of means for this case. All right. First of all, disclaimer, I got this from some kind of book from somewhere, and when I plotted this function, it actually looks like this. I just want to say that this seemed a little silly to me. When I plotted this function t all the way from 0 to 8, I saw something that looked like this. Okay, so it actually does have a relative max in the p here, and this is in items, and the t here is in hours. This is supposed to represent the number of items that a worker has actually produced over that amount of time. So after 1 hour, they've made this many. After 4 hours, they've made that many. At some point, they've made as many as they could. And then what happens here? Why does it go down? They start breaking them after a while. If this is truly what's going to happen for my worker, I would have them stop their shift right here. Okay? Because after this relative max right here, what you're saying is the workers are starting to break the items, and so they have less overall production after 8 hours than after whatever this value is right here. So I think that's a little silly, but anyway, let's use calculus on it to locate the relative max, which is the time at which the most items will have been produced. And then we're going to look for another special point. We're going to look for the point of diminishing returns. That's going to be a place where this function's graph changes from concave up to concave down. Hopefully now you're getting kind of comfortable recognizing the visuals for those. Concave up right here, does everybody see it? Concave down, that looks like you're under an umbrella there. That means there's an inflection point somewhere between, because you can't jump from positive second derivative to negative second derivative without going through a 0 second derivative. So I really want to find the point of diminishing returns, and then we'll talk about what it means. Okay, so why don't we take some derivatives and see how it goes on there. All right, and so first we'll start with p prime. And you get p prime of t is equal to 216 plus 18t minus 9t squared. All right, so if you were going to locate the relative extrema, such as this relative maximum right here, what is this? T equals what? The answer would be someplace where the derivative equals 0. And that's because I can see the horizontal tangent that's synonymous with the relative extrema. Okay, so if you want to solve this out, go right ahead. Quadratic formula, I'd rather not. Factoring looks a little hard, but it turns out if you divide everything by -9, which you can because it's 0 on that side, it'll stay 0, you're going to get some quadratic that's a little bit easier to manage. The quadratic is going to look like this after you've divided everything by -9. And once again, that's fair to do as long as you're solving it equals to 0, because 0 over -9 is still 0. Okay, and the reason I did that is because then I can kind of see that this is going to factor t minus 6, t plus 4, and so the answers are going to be t equals 6 and minus 4. Now t equals minus 4 is not in the domain. Remember the domain here was to be between 0 and 8 hours, And so minus 4 doesn't count, but 6 does count. And I'll leave this up to you guys to do, but if you created the sign number line, the p prime sign number line, you would see that by the first derivative test, the function's going up, it hits 0, it's going down, and so I do have a relative max right there. And if this truly is what it says it is, then I would tell you to let your workers off at 6, because after 6 hours they are not doing good anymore. I don't know what they're doing to your items. Okay, so that's just a caveat. But what I really want to hunt for here is the point of diminishing returns. It's going to be the place where it changes. You can see concave up is happening here. You can see concave down is happening here. Somewhere in here, t equals what? It's going to be the place where I have my point of diminishing returns. It's going to be the place where the marginal quantity is maximized. The derivative quantity, p prime. What is p prime exactly? If p is the number of items that have been produced and t is time in hours, let's try to interpret p prime, and that way once we put a little meaning to it, we will really appreciate locating the place at which it's maximized, point of diminishing returns. Okay, p prime of t is in, here we go again with the units, p prime of t is in y units over x units. So it's in number of items per hour. It's always the same, y units over x units. As long as you figure those out, y units, x units, derivative is that ratio, okay? And the reason I care is because then I can interpret what the p prime is. Items per hour, so that means that if I let my workers work for 1 more hour, they will make p prime more items, okay? So this is actually the production rate. I can see that. This is the interpretation, is p prime is the production rate in items per hour. That makes sense. If I was going to say what's the production rate, I'll say, I don't know, 100 items an hour or something like that. So that's why I want to get the units. This is the production rate. My question is not when is the function maximized. I already answered that question. The total production is maximized here. My question is when is production rate maximized? Okay, because I want to know that those workers are working, and I also would like to know exactly when are they working at their fastest rate. When is their production rate, the number of items they make per hour, as high as it can possibly be? And if I think back to slopes of the tangent line, I haven't drawn many tangent lines lately. The slope of this tangent line is the rate of production. How many items per hour are they making? Look, they're doing more, more, more. See how that slope's getting higher and higher? But now all of a sudden the slope got lower and lower. And actually the slope's 0 there. So, and then it gets negative, so you better let them off of work now. That's when the tangent line is as steep as it possibly will be. Okay, so right here, the point of diminishing returns is the place where the tangent line is as steep as it possibly will be. Tangent line is maximized at the point of diminishing returns, okay? So let's try to find that. Let's see, we took the first derivative, set that equal to 0. How about let's go a little further and take the second derivative, set that equal to 0. So that's going to be p prime of t equals 18 minus 18t equals 0. Solve that out. That's a pretty easy linear function to work with. So t equals 1 hour. This is going to be my point of diminishing returns. And you can see that answers the question right here. T equals 1 hour on the graph. My production rate is maximized at t is equal to 1. Okay? Now, I'll leave the rest of this problem for you to do on your own. Technically, to make sure that that is a true inflection point, which will make it the point of diminishing returns, you must show that the concavity changes. And you'll want to do that analytically by making the sign number line. Okay? So it looks like here, if you had the sign p double prime sign, you've got it equal to 0 at t equals 1. Before that, it's concave up. After that, it's concave down. You can go ahead and confirm that with test points. That shouldn't take you too long, but you can also confirm it on the graph here. And the meaning of it is, that's when my workers are working at their fastest rate. So let's tell a little story. Everybody comes in, we're all like, hey, what's up? You know, we put our lunch away in the fridge and we're kind of messing around. So what do we got to do today? After an hour, that's when we really hit our groove. This is when we're making the most things per hour that we're possibly going to make. And then we're kind of getting tired, start getting chatty, got to go to the bathroom, take a break. And then this is the most things that we're going to make that day, period. After that, I don't know what we're doing, breaking them or putting in our pockets, taking them home. Something happened over there. Don't even go over there. But this is a nice place to know. For instance, if I was your mean old boss, I would say no breaks for the first 2 hours. Because I know that you guys have your maximum production rate between hours 0 and 2. Particularly, your maximum production rate is at T equals 1. So nobody's allowed to take their break 1 hour after your shift begins. And that's efficiency. All right.